we pretty much have a couple more examples to go in this chapter, which is actually the final chapter there. I think that's going to be on our next exam, if I'm not mistaken. So what we're going to do is we're going to finish up those couple examples, kind of go through it, and I think we might also continue on into the next chapter just to keep us on pace for a little bit. Then we'll stop, and obviously the rest of the time for lab, you could continue to work on the electrochemistry one. And I think we'll start the galvanic cell experiment on Thursday. So that's sort of the little change around that we'll do here. All right. So the last part of sort of the electrochemistry chapter that we've been talking about is electrolysis. And electrolysis really is, as we mentioned earlier, they're sort of applying an electrical current to make sort of a non-spontaneous process actually occur. So as we talked about a couple of those examples in those slides previously, again, if you take something like sodium chloride, under sort of normal sort of conditions, we don't expect to get back sort of the components of it, like sodium liquid or molten sodium or something like that, or chlorine gas. Our water, we don't expect to get back hydrogen gas and oxygen gas by breaking it apart. But if you do sort of an electrical current and apply that, you're causing really a chemical reaction to occur, a chemical change to occur. You're really causing like a redox sort of reaction to occur. One of the sort of driving forces, if you maybe remember from previous semester, for why sort of reactions take place, there's kind of three major reasons why reactions sort of take place or chemical sort of changes take place. One is electron transfer, kind of like what we're talking about here. Other is the formation of water or the formation of a solids or precipitate. So those are like the three sort of driving forces as to sort of why reactions take place. By sort of applying that electrical current, you're allowing that sort of transfer of electrons situation to occur. There's sort of basic sort of steps in these sort of problems here that we follow, and I sort of outlined it there at the end of lecture. But I did want to kind of go through an actual example with you and sort of show you how to apply sort of these steps to it. So we're going to actually do, it might be out of order on your notes. So we're going to do actually the last example first, and then we'll come back to the water example there, or the sulfuric acid example. So in this particular case, we want to know how much calcium would we produce in an electrolysis cell uh, of molten calcium chloride if we had a current of 0.452 amps and we passed it basically through the cell for 1.5 hours. So remember that when we think about sort of the reactions, as we talked about earlier today, that we're sort of going opposite of what we naturally think about. So we're actually starting with calcium chloride, which means really what we're starting with is a calcium that has a +2 charge, and we're starting with a couple of chlorides. And we basically want to take them back to their natural state, which would be like calcium here, solid, and chlorine gas here. So when we look at it in that aspect, we could figure out our anode and cathode hopefully relatively easy. We could see that the calcium here is +2 going to our calcium solid, which is 0. Again, going from +2 to 0, meaning that this is going through reduction, and this would be our cathode in this electrolysis cell. While again, much like we saw earlier, our chloride going from -1 to 0, which would then mean that it is being oxidized and would be our anode in this electrolysis cell. So again, it's sometimes opposite sort of thinking, but remember, we're sort of kind of doing the opposite of a synthesis reaction. We're kind of bringing it back down through a decomposition reaction. So we're kind of working backwards of what we normally think about when we think about calcium chloride. So that's why what we see here again for our anode reaction is our chloride going from -1 to 0, our calcium, which is starting at a +2 charge, going to 0. Any questions on that so far? So here we are really interested in just the calcium here. So it is just the calcium that we're interested in. So first off, we will need a couple of things. We will need to figure out the amperage, which they gave us, which is 0.452 amps. Remember that as we saw previously, an amperage is a coulomb over seconds, which is maybe the units you may want to use that in, so you can see everything sort of canceling out. And what that would mean is you have 0.452 coulombs per second. That's good because it does give us our time. Our time here is 1.5 hours, but the units that we have here from our amperage is in seconds, and this is hours. So again, like normal, we just want to make sure that everything in terms of units are okay. So we're going to convert that into seconds, and I believe there's 3,600 seconds in an hour. Those guys will cancel, and that will get us, I think, 5,400 seconds, if I'm not mistaken. 5,400 seconds. And again, really the reason why we need this guy in seconds is really for this part, right? So that everything cancels out. So if you remember, the first thing that we really want to do is just really take the current that it's running through the cell. We want to times it by how long it's running for. Again, we want to make sure it's in seconds so that they do cancel each other out. So if we multiply those two guys by each other, that is going to give us basically the unit of electrical charge for this cell, which would be 2440.8 coulombs. Any questions on that there? Now, if you remember sort of the way that we work this problem, once we get it to this point, this is where we can use Faraday's constant, which is our 96,500. And again, in this case, it is coulombs per mole of electron. And we're going to use that really as a conversion factor here to get us into moles of electrons. So if we do that, we want the coulombs to cancel. So the 96,500, which is Faraday's constant, goes on the bottom per mole of electron. The coulombs will cancel. And now we're at moles of electrons, which would be, in this case, I put the right amount of zeros there. Looks like, let's see, 2440.8 divided by 96,000, oops, 96,500 gets us 0.0253 moles of electrons. Any questions on any of those steps so far? So to rethink, we're basically taking our amperage times our time divided by our Faraday's constant. So those steps are pretty fairly standard in these type of problems. And again, the goal of those steps is to get us to moles of electrons. It's at this point where our half reactions come into play and why it's important, right, to have a sort of balanced half reactions and stuff like that. We're basically going to kind of do like a mole to mole relationship, pretty much like stoichiometry. So in this particular case, again, we're interested in calcium. So we will look at the calcium half reaction here. And from the calcium half reaction, we see that for every 2 moles of electrons there are, we get 1 mole of calcium. So just like stoichiometry, we can basically set up a mole to mole relationship here. And that's going to allow us to go from moles of electrons to moles of calcium, which is kind of what we're interested in. So that would be our next step here, 0.253 moles of electrons. Using that mole to mole relationship from the equation, 2 moles of electron, 1 mole of calcium gets us 0.0126 moles of calcium. we're not interested in really how many moles of calcium. Usually we're interested in grams. So at this point, it's now just a conversion between moles to grams, and we use the molar mass to do that from the periodic table. That looks like 4008 grams per mole. So that would be our final step here. And it would be 40.08 grams per mole of calcium. So we're going to multiply that by 40.08, going to get us maybe 0.50, we'll go 0.51, do a little bit of rounding here. 0.51 grams of calcium here would be produced in this particular case. So this means that if we ran the cell for, like it said, 1.5 hours, we kept it at 0.452 amperage in terms of the current, we should get out of that cell produced 0.51 grams of calcium. Any questions on that? Now, just to show you, in this particular case, it did not ask for chlorine gas, but we could have figured out how much chlorine gas we would produce as well. And basically, we would pick it up from this spot right here. So we would pick it up from the 0.253 moles of electrons, but we would then go to chlorine's half reaction here. And from there, we see that there is, for 1 mole of Cl2, you get 2 moles of electrons. So in this case, actually will come out pretty much the same. Not always the case, but we get 2 moles of electrons and 1 mole of Cl2 would give us 0.0126 moles of chlorine. If we were interested in, how many grams that would be, we could use the molar mass of chlorine, which would be 3545 times 2, 7090. And that would get us 0.0126 times that, 0.89 grams of chlorine gas would be produced. Most likely, though, if we were interested in the chlorine gas, we might want to figure out the volume, which would be nRT over P. You probably would be given some temperature, some pressure, R is a constant, and you could use the N that you had here in the box. And if you had the right information, you could also figure out the volume of chlorine gas that you would produce. Any questions on any of those steps there? Okay, so now that we did one here together, why don't you try one here? Let's go back to the one we skipped, which is actually in my case this way. There we go. So a current of 1.26 is passed through an electrolytic cell that containing sulfuric acid for 7.44 hours. Write the half cell reactions, I did it for you there on the bottom, and calculate the volume of the gases generated. So before you go off and just want to go, this is what I was saying before. There's no mention of water anywhere, but it's talking about that sulfuric acid solution. So that is really the electrolysis of water. So again, remember, it's done with some type of acid sort of solution, acid water, something like that, some acid added in there. So it's meaning that, and that's why we have the half reactions here for water, as you can see, being formed. So that means that what we're looking for is the volume of oxygen gas and hydrogen gas at STP. In case you don't remember, STP is standard temperature and pressure. And standard temperature and pressure means the temperature is 273 Kelvin and the pressure is 1 atmosphere. All right, so I think that's everything that you need. So take a few minutes here and figure out what is the volume of each of those gases that you end up with. 0.44 hours. We're looking for the volume of oxygen gas and hydrogen gas at STP. And as I mentioned before, STP being standard temperature and pressure. So again, that pressure being 1 atmosphere. temperature being 273 Kelvin. Okay, so in this case, we are going to be looking for the volume of a gas. So as I said before, very common, we will be using P v equals nRT to do that. Solving for V would be nRT over P. The pressure and the temperature is given to us here. We have R. So again, we sort of need to do the electrolysis part of the calculation there to get to our moles, really, of each of the gases. We could do it for oxygen, obviously, and also hydrogen as well. So we're going to start with sort of the basic sort of starting of this type of problem worded like this. We're going to take our current for how long we ran it for and basically times it by each other. So remember that 1.26A is the same as 1.26 coulombs per second. We are going to run it for 7.44 hours. So just like we talked about in the previous one, we want to make sure we don't have any issues with units. So we're going to, off the bat here, obviously convert this guy into seconds. Again, 3,600 seconds in an hour. And that is going to get us 7.44 times 3,600. Looks like 26,784. So that's sort of the first step here, really, to kind of get the electrical charge, really. So we're going to times this by 26,784. Again, the seconds here will cancel. That's going to leave us with our coulombs, which in this case looks like, what do we got there? 3,747.8 coulombs. Remember, though, that we do need to get to electrons so that we could use our half reactions here. And that is where Faraday's constant comes into play. So we're going to divide it by Faraday's constant, 96,500 coulombs per mole of electron here. And if we do that, divided by 96,500, gets us 0.3497 moles of electrons. Any questions up to that point there? Now, this is what's going to allow us, right, to go from moles of electrons to our moles of the oxygen gas, which we need. And in this particular case, also the moles of the hydrogen gas, which we need as well. So to get to the moles of oxygen gas, we would use our moles of electrons we just calculated. We would then go to the half reaction that involves oxygen or O2, and we can see that for every one O2, we do get 4 moles of oxygen. So we're going to use that as our conversion factor. Again, for every 1 mole of O2 from the half reaction, we get 4 moles of oxygen, 4 moles of electrons. So we're going to divide here by 4 moles of electrons to 1 mole of O2. And that will get us divided by 4, looks like 0.0874 moles of O2. We could do the exact same thing for our H2 because we know we need to get that guy as well. So for our moles of H2, we would start with our same moles of electrons. We would go to the half reaction that involves H2 and get our relationship. So this one, there is a little things going on. There is a 4 here on the outside that does get distributed to everybody. And if you distribute that 4 all the way across that half reaction, you end up with actually 2 moles of H2, gives you 4 moles of electrons. R, that's the same as 1 mole of H2 gives you 2 moles of electrons. You could use either one. Obviously, they both come out the same. Any questions on that one? So you do need to distribute that 4 across everybody there to get the balanced number of electrons, right, that's needed, so that everything cancels out correctly. And in that case, we'll just use the original one there, which would then be 4 moles of electrons, 2 moles of H2. And for our H2, that's going to get us 0.3497 times 2 divided by 4, 0.175, we'll round it to. 0.175 moles of H2. Any questions on either of those parts of the calculation? All right, so really, if we think about sort of what we got going on, we have now found really the missing piece there for each of these. So we can now use the ideal gas law and solve for the volume of each of these gases. Again, we could do it separately. So the volume of, we'll go with O2 first, is going to equal nRT over P. We want to make sure we use our moles of our O2, which is 0.0874 moles. We also want to make sure that we use the gas constant, the correct value here for the ideal gas law. We've been using the 8.314 version a lot, but again, we want to go back to the correct one here, which is the 0.082, and temperature being 273 Kelvin, all divided by our pressure, which is 1 atmosphere because it is standard pressure. And that gives us 0.0874 times 0.08206 times 273, going to give us like a 1.96 liters of O2 would be produced here. Any questions on that one there? Now that we have the volume of O2, put a better box around it. There we go. We can now pretty much go exactly into that ideal gas law if you like, and pretty much just do the same thing now for hydrogen. Obviously, in this case, we would want to use the moles of hydrogen in this case, which is 0.175 moles. Everything else going to pretty much be identical to what we just did above there. All divided by 1 atmosphere. And that is going to get us 0.175 times 0.08206 times 273, gives us like a 3.92 liters of H2 in this case. First off, any questions on that? By the way, just a reminder of a throwback maybe to gas laws. You might also know perhaps or remember that you don't even have to really use the ideal gas law here because we're at STP. 1 mole of any gas will equal 22.414 liters. Again, you can use that conversion at STP. So for example, if we wanted the volume of H2, we could actually just take the moles of H2 and pretty much times it by 22.414 liters is a mole, and you will end up with 3.92 liters. So, yeah, old rules still apply, and a reminder that you can only use that conversion right there if it is at STP conditions. So if you're not, you do have to use the ideal gas law. But if not, you could always use the ideal gas law as we see in both of these cases. They both give you really the volume. So what this tells us is if we ran this cell for 7.44 hours at that amperage, this is the volume of oxygen gas and hydrogen gas that we would expect to be collected. Now, what do we see here? Well, if you look at the comparison of the amount of hydrogen gas that was collected versus the amount of oxygen gas, what you see is what we talked about previously, that you got twice as much hydrogen gas collected as you do oxygen gas, right? So if you times 1.96 by 2, you get that number right there. Any questions on electrolysis problems? So these are common electrolysis problems. I would say the sort of third type of electrolysis problem is kind of working backwards. Like you're told, hey, you ran this cell for a certain amount of time at 1.26 amps, and you collected 50 grams of calcium or something like that. How long did you run the cell for, and kind of working your way backwards. So that's the sort of opposite electrolysis sort of problem. They sort of give you how much you produce, and you have to work your way backwards to either figure out how long the cell ran for, or what the amperage was or the current was for that cell. So that's sort of a variation on the electrolysis sort of problem. Any questions on that? Okay, so like I mentioned before, that actually does wrap up this chapter, and I believe that means that that wraps up the material for the next exam, which is scheduled from 1 week from today. So that should still stay. So we'll take it during lab time, and it should cover this chapter and the one before it. So that should be thermodynamics, I think. So it should be thermodynamics and all the electrochemistry stuff that we talked about, including being able to balance redox reactions and all that kind of good stuff. Any questions on any of that? Okay. So like I said before, since we've kind of been lecturing a little bit here, we might as well go a little bit further for a little bit longer, just to kind of keep us on pace. So we will continue lecturing into the next chapter, which is chapter 19. And again, this will not be on the exam next week. This will be on, I guess we're now down to final information or stuff that will be on the final exam. Again, the next exam, if I am not mistaken, let me just double check, but I believe that's correct. That's what's on there. It is chapters 16 and 17. So that's the one we just finished. So that should be thermodynamics and electrochemistry. And again, it's on next week. So I guess that'll be the 20. Where are we at there? Maybe 24th. It should be, I believe. That's where we're at. So it should be on the 24th. Okay, so we're off now to sort of transition metals. We're actually down to, I think, just a few more chapters, or a couple more chapters to go, including this one here. So we're going to talk a little bit about, in this chapter, transition metals and coordination compounds. We're actually going to talk about complex ions more, and sort of how to name them and stuff like that. But we're going to first start off this chapter sort of reviewing maybe some stuff. And again, some of this stuff might be reviewed to you. You might have learned it last semester. We're going to talk about transition metals and some of the aspects of it and some trends. So hopefully everybody, again, will be sort of on the same page. So the first thing we're going to talk about is sort of what's referred to as effective nuclear charge. And effective nuclear charge is sometimes referred to as Z effective, and you might have talked about this previously as well. But this is essentially the positive charge that's felt by the electrons, basically the positive charge that the electrons feel coming from the nucleus, right? So inside our nucleus, we have our protons, which are positively charged. We have our neutrons, which have no charge. And then we have our electrons that are out and about, sort of floating around, which are negatively charged. So for example, if we take something, say, like lithium, for example, we take something like lithium, it's got basically 3 electrons, and it's also got 3 protons. It has an electron configuration, 1s2, I'll write that right, try that again, 1s2, 2s1. And when we think about sort of what's happening, we basically have these electrons here in the lower energy level, sort of referred to as the core electrons. We have the higher energy level electrons, which are our valence electrons, right? Those are our guys that are involved in bonding and so forth. And if we think about sort of the arrangement, you got this kind of positive 3 nucleus happening. You got sort of your core electrons sitting there. And then, you got your sort of valence electron kind of sitting outward from it. Now, when we look at these guys, a couple of things are sort of happening. When we think about the core electrons that are sitting there, these guys, these sort of core electrons, they're really feeling the full force of that positive 3 charge. And one thing that you might remember or maybe not remember is positive negative attraction, right? That's electrostatic attraction. And it does, the strength of that increases with the charge. So something that's +3 and -3 is held together a lot stronger than something that's like -1 and +1. So these guys are really feeling that full force of it, right? But now when we think about sort of that electron that's on the outside there, our valence electron over here, right? Our valence electron is not necessarily feeling that full force of that positive 3 charge because there's a process which is sometimes referred to as shielding happening. And what is shielding? Well, these lower energy sort of electrons, they're closer to the nucleus, so they really do feel that full brunt of the positive charge. But in addition, they're actually kind of blocking that positive charge from getting all the way to the valence electron, for example, here. So it's kind of like in the movies, you go in, you sit down when you could just pick your seat, I suppose, and you got your nice center seat. You were there early, you were right there, you're happy. And then right before the movie comes in, somebody comes in with a big old hat, sits right in front of you, blocks off half of the screen. You can't see it. They just shielded the screen from you. So same idea here with this electron. You know, it's not really feeling that full force of that positive 3 charge. So what is it feeling? Well, we could do basically what is referred to as the effective or the effective nuclear charge that that electron is feeling by taking Z, which is the number of protons, the atomic number, minus the number of core electrons, which in this example here would be 2. So +3 minus 2 gives you a +1 charge. So this valence electron out here is not really feeling a sort of +3 attraction to the nucleus. It is really feeling a more +1 attraction to the nucleus. And that means it's not going to be held as tightly. Because it's not going to be held as tightly, it's why it's involved in bonding. It's able to be sort of given away, lost, shared, whatever may be happening, most likely lost in this case, because it's not really feeling as much of a strong charge. So what we see with Z effective is it sort of increases as we go across a period on the periodic table. And that's what we're looking at here. This is like period 3 on the periodic table going this way, going across it. These numbers are a little bit out of spot there, bringing everybody back. But what we see is an increase in sort of that effective nuclear charge. It gets larger. So what does that mean? As we go across that period, we actually see the radius get smaller. So what does that mean? It means that as we go across, we're building up a bigger positive charge in our nucleus. So even our higher electrons are going to feel more of that positive charge. And it's going to bring these lower electrons in, by default, bringing the rest of the electrons in as it increases that positive charge, making the whole radius get smaller. So because we have a lot more protons, even though those valence electrons are experiencing some shielding, it is still going to be a much higher positive charges they're filling than what they would see, you know, to the left on the periodic table. That's why as we go to the right on the periodic table, we typically hit guys that will hang on to their electrons, right? Because the size gets smaller, they're holding on to them tighter. There's a bigger positive charge as to the left of the periodic table, where things typically have a smaller number of protons in the nucleus, not holding those electrons as tightly and able to give them away a lot easier. And that's what we see here. Within a period, the Z effective increases, and we see that the radius gets smaller. So that's your normal sort of pattern that you're probably familiar with. Again, things get smaller as you go to the right, gets larger as you go to the left. And again, we're building up pretty much more and more protons as we go to the right, making that nucleus be more and more positive, and really as a whole kind of bringing everybody in closer to that nucleus because of the greater positive charge. So we're going to talk about transition metals, and hopefully you're familiar with sort of transition metals, but just in case you're not, this is pretty much where transition metals are on the periodic table. It's between group 2 and group 3. These are our transition metals. This guy right here is our first row transition metal, second, third, and fourth. Also, if you remember a couple of things about our transition metals, first off, they are the D block in terms of electron configuration. By the way, over here is the S block, right? And from here to here is the P block on the periodic table. That is group 1, that is group 2, 3, 4, 5, 6, 7, 8. What does S block, D block, and P block really represent? You can, if you know what you're doing, sort of count off electron configuration. S orbitals can hold a maximum of 2 electrons, like 1 and 2. P orbitals can hold a maximum of 6 electrons, like 1, 2, 3, 4, 5, and 6. D subshell could hold 10, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. And F, which are down here, can hold 14, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14 electrons. So if you know what you're doing, you can use the period numbers. You can literally count off electron configuration. This would be technically 1s1, 1s2, period 2, 2s2, 2s1, 2p1, all the way down to 2p6. This would be 3s2, 3p6. This would be 4s2. Also important to remember, though, transition metals and d orbitals don't occur until n is equal to 3, which means that this one, even though it's on period number 4, that is actually 3d. This guy would be 4d, 5d, and 6d coming down in terms of electron configuration. So, good to remember that. It doesn't necessarily go always in order. Also Fs, right? Fs don't start until 4th energy level. So that's 4F, and that is 5F in terms of electron configuration. These guys on the bottom are also transition metals. They're sometimes referred to as inner transition metals. They're referred to that because, technically speaking, if you follow the numbers, this guy right here should go right there after lanthanide, and this guy right here should go after actinide. And that's why they're lanthanides and actinides. They technically go in that order. If you follow the atomic number there, it goes from like 57 to 72 here between these two. And this guy is actually the row that goes in there. So they technically are transition metals. We don't really deal too much with those. We do see a little bit of it in nuclear chemistry. But other than that, not too much going on in terms of those guys. Other important things about transition metals is charges, as you're probably familiar with. These guys have a variable type of charge, which is why with type 2 sort of guys, we use Roman numerals, right? When we name these guys. Like Fe3 plus is iron, Roman numeral 3, right? Ion. There are a few, though, that are in the transition metal region that, although they are technically transition metals, they do not have variable charge. These guys right here, these three are pretty much have fixed charges. And that is zinc, which is always a charge of +2. That's cadmium, that's always a charge of +2. And then hang a left there to silver, always +1. So although they are transition metals, they do have that sort of fixed charge, which is sort of unusual for transition metals. Any questions on that stuff there? So within a group or a column there on the periodic table, transition metals do show very similar sort of properties. When they do form ionic compounds, they can have multiple oxidation states. And a lot of times these transition metals are often involved in complex ions. So we talked a little bit about complex ions when we did KF there in whatever chapter it was, 15 maybe. They are complex ion is really a metal that's in the middle there. And it has a bunch of guys that are attached to it, which are referred to as ligands, right? And if you remember, ligands are basically Lewis bases. And if you remember what a Lewis base is, it is something that will donate a pair of electrons, electron pair donor. So those are things like water. They got those electron pairs, something like ammonia also has electron pairs. Something that is negatively charged, like chloride, for example, has those electron pairs it could donate. So those are basically complex ions. They have that positive metal guy in the middle with those ligands that are there. And as we can see here, we have our cobalt, which is a transition metal. And we have these NH3s, which again have those pairs of electrons that are being donated. And when we think about complex ions, as we'll talk about in this chapter, it really is more of a Lewis acid base situation where these ligands, which in this case would be our NH3, are basically donating our pair of electrons over to our metal. And we get this kind of scary looking formula here that involves that transition metal and those ligands are attached. And most people go, that thing right there. I don't know how to name it. We will actually learn how to name this guy in this particular chapter as well. So you don't have to just go that thing right there. We'll know how to name it as something like hexamine cobalt 3 ion is basically what the name of that guy is. And obviously we'll go over the rules for naming those guys and the things that we'll talk about a little later on in this chapter. Remember, ionic compounds, a lot of them are sort of, do give different sort of colors of solutions because of the transition metal ion in the complex ion. It can absorb light at specific wavelength. Depending on sort of the ligands that are attached, the charge of the transition metal, you may get some different color solutions, even if you're dealing with, for example, the same metal. Like cobalt, for example, you could have a situation where cobalt is, depending on its oxidation state, sort of a pinkish sort of color solution. You could have a cobalt complex ion that's more blue in terms of color, depending on the situation. Many of these compounds are what are referred to as being paramagnetic. You might remember paramagnetic involves basically electrons and unpaired electrons. So the more unpaired electrons that you have, they're sometimes referred to as being paramagnetic. Again, electrons, right, have spin associated with them, as you might remember from talking about quantum numbers, the MS guy, the spin quantum number, where an electron could be plus or minus a half, right? And they sort of have their own sort of electrical sort of field and effect and stuff like that. So you can get a bunch of sort of non-bonding or unpaired electrons, and it'll be what is sometimes referred to as being paramagnetic. They're sort of paired off, which is when the electrons have the sort of opposite spins inside of a sort of orbital. That's what's referred to as being diamagnetic, right? So just to review again a little bit about electron configuration and transition metals, which is going to be a little bit important as well later on in this chapter when we talk about some things known as crystal field splitting. Hopefully you remember how to write electron configuration, but remember that most people learn sort of a zigzag sort of guy that you can recreate pretty easily for yourself, remembering that S's orbitals start on the first energy level, P's start on the second. D's start on the third energy level. And F start on the fourth energy level. And this is basically that zigzag thing that I'm pretty sure most people have seen some version of it. And it gives you sort of the correct electron configuration. You always start up here, and basically you come down and zigzag back and forth. With that and the understanding that, right, that S orbitals can only hold a maximum number of electrons of 2. The P subshells, because there's 3 different P subshells, each one can hold 2, 6 electrons. D subshell, there's 5 different of them, each one can hold 2, is 10 electrons. F subshell, there's 7 different ones, and each one can hold 2, which is 14 electrons. will allow you basically to write any electron configuration that you need. We just talked about a second ago about the sort of D blocks and S block and P block where they are on the periodic table. Um, so this is noble gas configuration. This is argon. And then you continue on with configuration 4s2, 3d3 for our V there, which is 23. Again, if you wrote it out, it'd be 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 3d3. And again, if you just take that part of the configuration there and just add up the top numbers, that's 2 and 2 is 4 and 6 is 10, and 2 more is 12 and 6 is 18. That is where argon's configuration comes from. And then the rest of it continuing on here. A reminder that when electrons go into the atom, which is normally how we write electron configuration, and if you follow sort of this order here, we do see that the 4s orbitals do get the electrons before the d orbitals. And typically speaking, that is what always happens with our transition metals. So if we look back on sort of the periodic table there, we have group 1 and 2, which is our S block. And then we have our D block, which is our transition metals. So these guys always get filled first, and then into the D block, which is our transition metals, are the ones that then get the electrons that are coming in. So when we do fill up those electrons, the s orbitals do get them first, and then we start filling, right, our d orbitals. Not to be confused that there is really, these guys are very close in energy to begin with. And once we actually do start, so actually filling the d orbitals, there's actually a switch in energy that occurs. And what ends up happening after we start filling the d orbitals with electrons is the 4s actually becomes higher in energy than the 3d. And that's important for when they lose electrons, they will actually lose electrons out of here first. But when they go into the S first and then the D. Now, most things do follow this sort of zigzag guide for electron configuration, as you learned. There are some exceptions, which I'm pretty sure you learned as well. These are probably the two common exceptions that you learned. And the exception is here with chromium, which is 24. Basically has one more electron up in the d orbital and one less electron up in the s orbital. Copper, which is 29, follows the same sort of exception. Extra sort of electron up in the d orbital and one less in the s orbital. Just found to be more experimentally stable that way. And it's able to be accomplished because essentially these orbitals are very close to one another to begin with. So it doesn't take a lot of sort of convincing to kind of move up and down. You may also know that if you look on the periodic table, below those guys, chromium and copper, there's actually a lot more exceptions to sort of the electron configuration as well, like silver is an exception. There's even some over there, like I think palladium and stuff, that have actually no electrons in the s orbitals. They've all been sort of promoted upwards. So it does sort of happen. There's a lot of exceptions, but most people were taught usually in like Chem 50-ish type class about those two. But again, there are several others kind of right below those guys on the periodic table that actually do have similar sort of exceptions to their electron configuration. Any questions on that there? Now, as I just alluded to a second ago, when these guys really do lose electrons, because of that switch that occurs when those electrons go in. So if we look at something like Ti, it's got like these electrons, 3D, and it's got 1, 2 electrons. And for Ti with no charge, this is again, that's the last part of the configuration, how it looks. But because we started filling those d orbitals, what ends up happening, as I mentioned before, is there's sort of a switch in terms of the energy, and the 4s orbitals actually get higher in energy than my d. Squeeze it over here. So when Ti, for example, becomes a positive 3 charge, the difference between these two things is that it has lost 3 electrons. So where do those electrons come from? Well, we typically lose electrons from the highest energy level first, which in this case is actually the s orbitals are always the first ones that basically come off. If we only lose 2 electrons in this case, we're still short 1, which means at that point, there's no more electrons up here in the s because they're all gone. The next highest would be then the d, and we would take one of those guys out. And we end up with an electron configuration as we see over here, basically 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and this was 3d2. So we are going to lose 2 out of there and 1 out of there, bringing us to what we see down here, which is our argon 3d1 that's left over. So Ti with a +3 charge again would have basically 1d orbital, 1d electron left in it. Any questions on that there? And that happens with all transition metals. They always lose the s electrons first, and then if they need to lose more, then they again delve into the d orbitals at that point. So why don't you try one here? What is the electron configuration for nickel with a +4 charge? And while we're at it, why don't you also do iron with a +3 charge? So take a second there and write the electron configuration for each of them. Atomic number for iron, in case you don't have a periodic table, is 26. And the atomic number for nickel is 28. All right, so take a couple minutes to see what you come up with. We'll just start with nickel, and since nickel is 28, we'll do nickel with no charge just to kind of make sure we understand where everybody's coming from. If we went all the way out there, 1s2, 2s2, 2p6, 3s2, 3p6, that would then be 4s2 and 3d8 happening there. At this point, nickel has a +4 charge. So nickel with a +4 charge means that it has lost 4 electrons. So again, the 2 electrons will come out of the s orbitals first because they are highest in energy. That's only 2 electrons. We then need to dig out basically 2 more electrons out of there, yielding us a 1s2, 2s2, 2p6, 3s2, 3p6, and 3d6 as our electron configuration, our argon 3d6. Any questions on that particular one there? And obviously, if we do the same thing here for our iron, if we just start with iron with no charge, going to yield us 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and 2, 4, 6, 3d6. Iron, obviously, here with a +3 charge means that it lost 3 electrons. So same are going to come out of there, are 2. Then we still need to take 1 out of there, yielding us 1s2, 2s2, 2p6, 3s2, 3p6, 3d5 are again argon 3d5. Any questions on how to write electron configuration for transition metals? Again, we're going to see sort of understanding how to do that. It's going to be important because you will need to, later in this chapter, be able to distribute these electrons correctly in certain situations. So you need to be able to figure out really how many d electrons a transition metal ion would have. Any questions on that there? Okay, so we're just going to talk about, again, some properties here for transition metals. Obviously, they can have multiple charges. They also can have multiple oxidation states. So as we talked about before, oxidation states are not necessarily always the charge we associate with things. And as you can see, certain things have a lot of different oxidation states. We do see as we go, this is our first row transition metals, starting there, going across the periodic table. We do see sort of an increase in oxidation number as we go this way, and kind of comes down the other way. We do see that for the most part, plus twos, plus threes are very common oxidation numbers for our transition metals. And as we're experiencing in our sort of electrochemistry experiment and stuff, we do see Mn here, right, can have a ton of different sort of oxidation numbers. We got there's like 6 different types, and it's really dependent on obviously what it is bound to and so forth. But again, most common ones, kind of twos, threes is usually what we come across, but they can be relatively large, some of them. This is a table of ionization energy. So just a reminder of what ionization energy is. It is basically the energy needed to remove an electron from the gas phase, right? So when we remove an electron, right, it becomes positively charged, which is basically what ionization energy tells us is kind of our cation formation, right? When we lose electrons, we're going to become positively charged. The general trend that we see, as you might remember, is it does increase as you go to the right and up on the periodic table, and decrease as you go left and down on the periodic table. The one thing that you might not realize or might not remember is that when we talk about ionization energy and we talk about things losing electrons, they actually do lose electrons basically one at a time. Um, and for every electron that they lose, there's an ionization energy associated with it. So, for example, if we looked at something like sodium, first thing that would happen is sodium would lose one electron. And that would be the first ionization energy. Then, perhaps the sodium that lost an electron would lose a second electron. And that would be known as the second ionization energy. If we looked at something, for example, like magnesium, magnesium first would lose one electron. And again, that would be our first ionization energy. Then magnesium would lose a second electron. That would be our second ionization energy. Then maybe magnesium wants to lose a third electron. That would be our third ionization energy. So for every electron that we lose, we basically have an ionization energy associated with it. So you may be saying to yourself, wait a sec, I know sodium is group 1. It only forms a +1 charge. I thought that is definitely what happens. And the answer is yes, you're right. It only forms a +1 charge. Why does it only form a +1 charge? Well, let's take a look at something like sodium. If we look at something like sodium, sodium basically has one valence electron, right? And when we lose that one valence electron, it only takes about 495 kilojoules per mole, right? So if you take a look at its configuration, 1s2, 2s2, 2p6, 3s1. So when we lose that first one, that is that, right? That is our valence electron. That's our outermost electron furthest away from the nucleus, as we talked about, not held as tightly because of, the Z effective. Here's our core electrons, which are definitely going to be held a lot tighter. And we see that in looking at the energy required to remove that second electron. It goes from 495 for the first electron to now about 4,500, 4,600, almost 10 times the amount of energy required to try to pull off that second electron from sodium, which is now a core electron. Don't forget, as soon as you lose that first electron, everybody's going to come in closer to begin with because the electron cloud now just got smaller. So all the electrons that were close to begin with are now going to find themselves even closer because of that. And that's why something like sodium, it really doesn't happen because it's just an enormous amount of energy under normal conditions. You're not going to find a sodium that's going to be able to do that. And that's why we think about sodium. It is only going to make a +1 charge because of the enormous amount of energy to try to rip apart that sort of core electron. It just really doesn't happen in that case. Now, when we look at magnesium, you may also be saying to yourself, wait, magnesium is group 2, which means it also only makes a +2 charge. So if we look at magnesium, that is 735, not too bad to take away that first electron. And if we think about it as configuration 1s2, 2s2, 2p6, 3s2, when we take away that first electron, we still have one more valence electron to go. You can see it's getting a little bit harder to remove that one. It's now up to about twice as much energy to take off the second electron, which would require this step. And now we're out of valence electrons. We have now moved back to our core electrons, which from the beginning, again, you can see is about 10 times the amount of energy from the first electron to try to remove this guy. Not going to happen in the case of magnesium either, because we're now into our core electrons at that point, and we won't do that. So that's typically what you see. Again, aluminum doing okay, but then a tremendous jump to try to get rid of that fourth electron, which is why, again, it doesn't typically occur. So ionization energy, first off, again, increases in general from left to right on the periodic table, decreases as you go down. And it also increases every time you take off an electron. So if you remove the first electron, the second ionization energy should be bigger than the first. The third ionization energy is usually larger than the second, and so forth. So it gets much harder and harder to remove an electron. Again, every time you take an electron off, you're getting smaller and smaller, which means those outer electrons are now closer to that nucleus and are going to be held a lot tighter because of that. Any questions on ionization energy? Here's a bunch of information about transition metals, which you should memorize. Everything on this chart, I'm just kidding. But some of the stuff you probably should know. So we talked about our electron configuration. We talked about our couple of sort of exceptions there in the first row, transition metals, where there's that, there it is. We also talked about our ionization energy here. And again, this is first, second, and third. And you can see the general trend we just talked about going from first, second to third. We see an increase in ionization energy every time we take off an electron. We also see that increase going to the right on the periodic table, again getting harder to remove the electrons. Remember that effective charge increases as we go to the right, overall size decreases as you go to the right on the periodic table. All the things are basically making electrons being held a lot tighter as you go to the right. We also see in general density sort of increasing to the right. We also see that melting points also are sort of decreasing as you go to the right as well. This is just a graph of what we were talking about a second ago. Red dots are our first ionization energy, blue dots are our third, and again you can see a much larger third ionization energy taking off that third electron versus taking off that first electron. In case you missed it and you wanted the second one in there, we see that general trend as we just talked about as well, increasing every time we take off an electron. Another important sort of aspect or sort of trend is what's known as electron affinity. Electron affinity should not be confused with electronegativity. They are different things. Electronegativity is the ability of an atom to bring electrons towards itself. Electron affinity does mean, do you like something, right? So if you have a pretty good affinity for something, you kind of like it. But it's basically the change in energy that occurs when an electron is accepted by an atom. So what happens when an electron is accepted? That is when we form a negative guy, which is an anion. So kind of electron affinity is a measure of, how you form anions. Why what we were just talking about ionization energy is really what happens when we form cations, right? So these are the things that are happening. in general, the general trend on the periodic table for electron affinity is it does increase as you go to the right and decrease as you go down. It's not perfect, as you can see here in group 7. This would be group 7 on the periodic table. It generally increases as you go up, but then we kind of go backwards a little bit here with the last one. So it's not a perfect trend in terms of increasing and decreasing, but that's sort of the general trend that we see. And it does make sense if you think about just location of everybody, right? On the top right of the periodic tables are non-metals, and then we basically have metals over here. So as we go up and to the right, we have things that pretty much are much smaller, which means they're holding onto their electrons tighter. They have more protons, which helps them to hold onto their electrons tighter. They also have a very high electron affinity, which means that they are attracted to electrons. They have a high electronegativity, which means they can bring electrons towards themselves. And all those things, pretty much as you probably have talked about before, is why we typically see nonmetals become negatively charged. And metals have pretty much all the opposite sort of arrangements, if you will. And that's why we typically think of metals as becoming positively charged and cations. Any questions on that there? Here's another table of some of the similar sort of stuff we just talked about. This is the relative reducing ability here of our first row transition metals. And you may be saying, wait a sec, this seems a little wrong. Isn't reducing ability, something that's going to be my cathode, right? And you would say this guy is more positive, so he's going to be my cathode, and it's not. Reducing ability means it's like a reducing agent, which means that going this way, this is the thing that's most likely going to be oxidized. Now, going the other way is the thing that's most likely going to be reduced. And you may look at these numbers and go, wait a sec, I thought the more positive guy was my cathode and getting reduced. And it is. The importance, though, is when you look at these half reactions, these half reactions are not reduction reactions, which means they're not SRP reactions. They are actually oxidation reactions, these guys. We know that because the electrons are on the product side, sometimes referred to as standard oxidation potential. Now, if we wanted to turn all these guys into SRP values, right? What would we do? We would basically reverse these reactions. When we reverse these reactions, the sign here would become opposite, which means if we reverse all these reactions, for example, the first one, and we wrote it as a reduction reaction, the E value would become negative 2.08. So all these guys would become negative all the way down, and the last guy there would become positive. And that does make sense based on what we talked about, which means the copper would be more positive, and it would be our cathode, and this guy would be our anode, right? And that is matching up with what we see here. Any questions on that one there? So here's a chart of the atomic radius for those guys. And again, we do see sort of a decrease as we go to the right on the periodic table for all of our transition metals. This is our first row, second row transition metals, third row, and we do see sort of that trend. It gets sort of bigger as we go up on the periodic table, or smaller as you go down, whichever way you want to look at it. In case you're not sure what these guys look like in the first row transition metal, these are some pictures of those transition metals and sort of what they look like. And again, they can have a lot of different sort of oxidation states, make up different numbers of types of complex ions. So these are some ions that they are. And again, you don't have to memorize any of these, but you can see just from the table here, for example, they all contain vanadium, which some are yellow, some are blue, some are violet, depending on sort of the charge in solution, their oxidation state. Here are some chromium compounds, again, greens, blues, orange, yellows, reds, depending on oxidation states and what's happening there. And again, same thing here, some pinks, some browns, some purples with our manganese. And again, iron here, depending on sort of what it's hooked up with, gives us a variety of sort of charges and also colors that appear in solutions. Some of these complex ions, which is what some of these guys are, we're going to talk about here in this chapter about how to properly name them and go about them. Any questions on sort of the transition metals, trends, and that type of stuff? Okay, so we will stop lecturing there. I think that was a good little